Hi and welcome to this last video in the series on sequences and series, and in this one we're going to look at recurrence definitions, which is just another way of being able to define rules to describe our sequences. And as well as doing that, along the way we're going to mention something called the period of a sequence, but we'll get to that right at the end. So here we go, recurrence definitions. If we have a think about a couple of the sequences we've seen previously, that one is an arithmetic progression, so with our start first value 8 and a common difference of 5. That one there is a geometric progression with first term 6 and a common ratio 3/4. What we're going to do is just take those and describe them or define them in a slightly different way. Because what we can do is like each term in a sequence relies on the term previously. So what we're going to do is change the notation slightly. So we're going to go for this u with a subscript n, describe each term. So the first term in the sequence would be u1. The second term would be u2, u3, and the other term would be un. Now, the key to this is we're being able to describe how do we define the term after the one that we're currently working with. Now that, we're going to describe that as un plus 1. So if this is the term that we're currently on, this is the one that follows it. So, our AP is going to transform. We're going to say, well, the next term in the sequence, if we know one of the terms, the following term is simply going to be the one we currently know, un, and then add on 5 because we've got a difference of 5. Now, that would pretty much describe any sequence that goes up in 5. It didn't have to be the specific one we're talking about. What we need to do to nail it down to be that specific one, starting 8, 13, 18, 23 and going on, is we've got to be able to have our value for our first term. So what we do is with our definition, we have the first term. So u1, we're told, is 8. And then this bit now says the next term is the one before it plus 5. And so there's the definition of our AP. And a similar thing with our GP. What we've got is our next term is going to be our current term times by 3/4. And the first term in our sequence is going to be 6. So what we've got now is our sequences that we've dealt with before, but they're just now defined in terms of following on from one term to the next term. But the key thing is, of course, that we have to have also that first term so we know where to start our sequence. So that's an important part of our definition. Right, let's have a look at a few examples. So what we've got here is 2 to do. So let's start off with the first one. We're told that the next term, un plus 1, is 3 times the current term squared and then take off 5. And we're told this sequence is going to start with the first term being 1. So, first 5 terms, u1 is 1. Now, when n is worth 1, un plus 1 is therefore 2. So for this second term in the sequence, we're working with a value of n within our definition. So our value here and here, n is going to be worth 1, which means this is u1, this one here is u2. So what we need to do is 3 times un, where n is 1, which is u1, then take off 5. So we're doing 3 times 1 squared, take off 5, and there's the minus 2. There's our next term. And then for the next one, n is worth 2. So now we've got to do 3 times u2 squared minus 5. So u3 is going to be 3 times u2 squared minus 5. There we go. And so that gives us 3 times 4, which is 12. Take off the 5. There's 7. And on we go when n is worth 3. So un plus 1 is u4. And that means I've got to do 3 times u3 squared minus 5. u3 being 7, so we need 3 times 7 squared minus the 5. So that's 142. Okay, and then the final one, n is worth 4. So we're doing u5. And that's going to be 3 times the previous term. So 3 times 142 squared. Take off the 5. And there we've got 60,487. And there you go, there's the first 5 terms in our sequence. And moving swiftly on to part B. Now this one, a little bit more complicated again, because we've got this un plus 2 equals 4 un plus 1 minus 3 un, and we're given 2 numbers. So essentially what this one's doing is using the previous 2 terms to be able to describe the next term. So what we need here is, to get to this term here, we need 4 times the previous term, take off 3 times the one before that. So that's why we've been given u1 and u2 as starting values. So u1 is 3, we already got that. u2, we're given that one. Okay, now let's go for u3. that's when n is worth 1. So that's why that's un plus 1. And so this thing here, 4 times the previous term, so 4 times u2, take away 3 times u1, plug in the numbers. There we go. And we end up with minus 1. So I hope you can see we're just using the previous 2 terms this time. So on we go to the next one, u4, slopes are when n is worth 2. Hopefully you can see if n is worth 2, that's why this bit here, un plus 2, becomes u4. And so we simply need 4 lots of u3 minus 3 lots of u2. There they go. And that leaves us with minus 10. And then the 5th term in the series is simply going to be that one, 4 times minus 10 minus 3 times minus 1, and that gives us minus 37. And so there are the first 5 terms in that series. So it's a little bit about kind of definitions and just getting used to kind of what the subscripts mean and how it all links together. But once you get familiar with it, it's not too much to worry about. Okay, having said that, you can get some questions that look a little bit more scary. So here we go. Let's have a go at this one. So we're told that the first term in the sequence is 1. We're told the next term is the previous term times by the previous term plus some value, this thing k, and we're told k is a constant where k is not equal to 0. So we're going to do the whole thing in terms of k. So here we go. I'm going to find u2 in terms of k. So u2 equals u1 bracket u1 plus k, and we're told in the start that the first term u1 is 1. So we end up with that, so therefore u2 is simply just 1 plus k. Now that's fairly straightforward, but now we're starting to deal with all our terms in terms of k, and it gets a little bit complex, and we're told that u3 is also 1. We've got to find out what k is. So we're going to need to come up with a definition for u3. So here we go, u3, there it is, u2 bracket u2 plus k, and we know what u2 is because we've found that part A, so let's plug that in. So u2 is 1 plus k, there it is there it is as well. So we've got that, and clearly we're working towards a quadratic here. Do some multiplying out, bit of tidying up, bit of solving. This is where we get to the point where quadratic, we've got 2 answers, but we're thinking, well, which one of those 2 answers is the correct one? Well, if you have a look back in the start of the question, we've got k cannot equal 0, that's why that's there. So that leaves us with k equals minus 3 over 2. And on we go to part C, where it says evaluate the sum of the first 100 terms. You might be looking at this in exam thinking, my crikey, that's going to be a bit of a job, a bit of a mission. But it's always a good idea to have a look at the number of marks available, because I suspect something like this would only be worth a couple of marks because there's going to be a shortcut somewhere along the way. We just have to find it. So the way to proceed with these, I find, is to just start thinking about subsequent terms and looking for patterns and looking for where we can make a bit of a shortcut. So if we've got u1 equals 1, we know that k is minus 3 over 2, so we can start working out, and if we find that u2 equals minus a half, and then if we put that back into our recursive definition to find u3, and that gives us u3 equals 1, and clearly we're back to this one again, so that means u4 has got to be minus a half, and so on and so on. So this recursive definition just generates a sequence of numbers that goes 1 minus half, 1 minus half, 1 minus half, and there's our shortcut, because now we can see if we take those two and add them together, we get a half. We take those two, add them together, we get a half. So all I need to do, rather than adding up 100 separate terms, is just say, well, all I've got there now is 50 lots of a half, because I'm going to have 50 pairs of numbers that add to a half. So the sum of the first 25 terms, the sum of the first 100 terms in that sequence is going to be 25. And there we go. Right, last thing we need to talk about is periodic sequences, and we saw one of those actually in the previous slide. A periodic sequence is one where terms keep repeating. So we had the previous sequence, there it was, and so we say we've got a sequence there, it repeats every 2 terms, so that's got a period of order 2. Okay, so it goes 1 minus half, 1 minus half, and so on and so forth. And so when we get something like that, trying to find summations of those kind of things become easier if we can figure out what the period is and what the sum of the terms is within that particular period. Okay, so here we go. We've got a recursive definition. So u1 equals 2, u2 equals 5, and then we've got the next next but one term, un plus 2 equals un plus 1 all over un, and that probably makes a lot more sense to read than it does to hear me say it. And what we've got to do is, as we say, we're told it's periodic, we've got to find the order of the sequence and then prove that it's periodic for any values of u1 or u2. So first part I think we're going to do numerically, the second part we're going to have a crack at it algebraically. So here we go, u1, u2, not a problem. u3 is going to be, so there we've got the previous term, plus 1 divided by the one before it, so you can see what's happening there. So that gives us 3. u4, and again we put the term, so we've got 3, that term there, it's 3 plus 1 divided by 5, which is 4/5. Go again, so we've now got 4/5 plus 1 all divided by 3, which gives us 3/5. And then keep going, because I'm not seeing any repeating factors yet, so I'm not sure how far this is going to go. So we've got now 3/5 plus 1 all divided by 4/5. Okay, now we're starting to see it, because now we're back to 2. And clearly, if I put 2 into that, now I say clearly, we haven't proved that will give us 5, because these were just 2 terms that were given at the start. So I think we do need to just, if we put 2 into this sequence, does it give us 5? 2 plus 1 divided by 3/5. Happy days, yes it does. And now we're nice and convinced that this thing is going to be periodic, because we're now going to get 2, 5, 3, 4/5, 3/5, 2, 5, 3, 4/5, 3/5, and so on. Right, so that means we've got a period and it repeats every 5 terms. So we've got a period of order 5. So there we go, first part done. It said find the order of the sequence, and we've managed that. Furthermore, prove it's periodic for any values of u1 or u2. Okay, so let's do this generically, algebraically, and let's start off by calling u1 A, u2, we'll call it B, and let's just go through exactly the same process as we did before and see what happens. So u3 is going to be b plus 1 over a, u4 is going to be b plus 1 over a plus 1, and then divide that by b, and do a bit of tidying up on that. We end up with that fraction there, and that's about as tidy as we can make it. And now I'm starting to get a little bit of a sense of dread, because you can see we're going to end up with some quite awkward looking fractions along the way, but we will persevere nonetheless. Here we go, u5 is going to be this one here, a plus b plus 1 all over ab, then add on 1, and then divide by un, which is going to be this one here, b plus 1 over a. So we get that. Do some tidying up on the top. I've got to be honest, I don't like fractions stacking up within fractions, so what I've done is written it as 2 separate fractions. This first one here is our numerator. This second one here is our denominator. But as you can do, I've gone for the old kind of KFC, keep flip change. We're dividing fractions, so let's just flip it upside down and do it as a multiply. Okay, so now what we're going to do, so that I'm hoping it's going to, well in fact I know it's going to cancel. So we can do a bit of factorising on the top. This is not immediately obvious, but we can factorise on the top, so that left hand fraction a plus b plus 1 plus ab is a plus 1 brackets b plus 1, and now you can see some cancels going to happen. I can cancel the b plus 1s, thank the good Lord. I can cancel the a's, and that makes that fraction a whole lot more simple. Phew. Right, so that's u5. What we've got to do, we are looking for this to become periodic, so we're looking for this to get back to a term at some point being a and a term at some point being b. We're going to have to keep going. We're at u5. If we remember rightly from the previous slide, this is when it started repeating, so hopefully, let's see what happens. There we go, we've got a plus 1 over b plus 1, and then the term prior to that, this one here, is u4. Again, do some tidying out, separate the fractions out, do the old keep flip change. You can see straight away we've got some cancelling will happen there, and some b's are going to cancel, and lo and behold, there it is, that's the result we were looking for. The next term is a, so there's the start of our next period, our next repeating sequence. And what we've got to do now is, same as we did last time, was prove that our next term, so we've got to go to u7, we've got to prove that becomes b. So what we've now got is a plus 1 over this one here, a plus 1 over b. There it is. Okay, that's just my way of dealing with fractions like that. I mean, you might be able to just spot that straight away, but for me it's a bit of the old flipping bit, and then clearly do some cancelling, and lo and behold, happy days, there is the result that we wanted. So what we can see is that regardless of what values we use, it is always going to be periodic, and that period is going to be of order 5. Sorted.